So this time we're going to talk about Taylor polynomials and Maclaurin polynomials. So what a Taylor polynomial is, it's an approximation of the derivative at a certain point. So it's an approximation of a tangent line slope. And it's notated by this p sub n of x. So this is like the name of the polynomial. That's how you write it out. And this approximation is just a series of numbers that you add up all together. And the more numbers that you have in that series, not series as in like a sequence, a summation of a sequence, but a series as in like just a lot of numbers. Okay, so I don't want you to mix that up. So it's just a bunch of terms that you're adding up together. And the more terms you have, the better your approximation of the tangent line. So I'm going to write out some terms, and we can start to see a pattern develop in how Taylor polynomials are written out. So c is the number that you're finding the derivative approximation at. And for your first term of the polynomial, you're just going to plug that into the function directly. And then your second term, you're going to plug c into the derivative of that function. And then you're going to multiply it by x minus c. And then for your third term, you're going to have f double prime of c. And this is going to be over 2 factorial. And then now this x minus c is squared. So what is essentially happening is each time you increase in a term, you take another derivative of the function. So we start at the regular function, and then we go to the first derivative, and then we go to the second derivative, and then the one after this, we would go to the third derivative at c. And then another thing that's happening is this x minus c is also increasing, but the exponent is increasing. So right here, there's technically an x minus c to the 0 power, but you don't write that because anything to the 0 power is just 1. So there's an x minus c there to the 0 power. Let me move this so it makes more sense. Okay. And then here it's an x minus c to the first power, and then here you have an x minus c to the second power. So here, in our fourth term now, you're going to have an x minus c to the third power. And then another thing that's happening is we have this factorial here. Now, right here, there's technically a 1 factorial under that f prime, but we don't write it because 1 factorial is just 1, and anything over 1 is just itself. So this, I guess this is 0 factorial, but like, I don't know what 0 factorial is. 0 factorial is just 0, but it's kind of, actually no, 0 factorial is 1, I think. Let me see. Yeah, 0 factorial equals 1. I can't tell you why. It's just a fact. So here you start at 0 factorial, and then you go to 1 factorial here, which is just 1. And then now you have a 2 factorial. So then obviously here you can think you have a 3 factorial. So this pattern just keeps on going on and on and on. And the way we write it out is f of n at c over n factorial, and then times x minus c to the n. So this is the format that this Taylor polynomial follows. And this n is just how many derivatives you want to take. So essentially how many terms of the Taylor polynomial you want to write out. So if this n equals 2, then you would come to this third term here, f double prime. Okay, so the pattern is, it looks complicated, but once you understand what the pattern is, it becomes much easier. So remember, you start at regular f with what number they want you to find the derivative at plugged in, and then you go to f prime, and then f double prime, and then f triple prime, and you just keep going until you get to that end that they want you to get to. And then you also have an x minus c. So you start at x minus c equaling x minus c to the 0, then you go to x minus c to the first, then to the second, then to the third. So you're all increasing chronologically. And then in the denominator of all of these, you have 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. So the three components you want to remember is the function, the x minus c, and the factorial. So that is in every single one of the terms. Just sometimes it's hidden because it would be redundant to write like a 1 factorial here. So that is the format of a Taylor polynomial. And then there's a special type of Taylor polynomial called a maclaurin polynomial. Maclaurin, that's what it looks like. And you still notate it with this p sub n of x because it's a type of Taylor polynomial. And a maclaurin polynomial is just when this c that you plug in to the function is a 0. So your first term, instead of f of c, it's just going to be f of 0. And then your second term, instead of f prime of c, you're just going to have f prime of 0. But now the reason this one is like differentiated is because all of these x minus c terms, you don't need that c part. So all you're doing is increasing the exponent of the x by 1 each time. So here we had like x to 0. Here we're going to have just x. And then our next term, we, let me write it like this. Take another derivative to become f double prime of 0, increase the factorial by 1 into 2 factorial, and then increase the exponent of the x by 1. So the maclaurin polynomials look a lot simpler than the Taylor polynomial. And let's just write out one more term so you can see. Increase the derivative by 1 again, increase the factorial by 1, increase the exponent in the x by 1, and then it's just going to keep on going, dot, dot, dot. So this time it would be f to the n of 0 over n factorial x to the n. So the only difference is the number you plug in is a 0 compared to c, and this part just doesn't have that c there because c is 0. So that's what a maclaurin polynomial is. Let's move this up. Yeah, that's fine. Okay. Now, what we're going to be asked is generally to use the polynomials to approximate some sort of number, because remember, these are approximations of a derivative at a point. Or we're going to be given a function and we want to be able to make a Taylor-Maclaurin polynomial out of it. Generally that, yeah. So let's just go over a nice simple example of a Maclaurin polynomial. Let's do Maclaurin first since it's simpler. So we have this function f of x equals e to the x, and our task is to make a Maclaurin polynomial out of it. So make into Maclaurin polynomial. So what we're going to do is the Maclaurin polynomial and Taylor polynomial, they all have derivatives of f in each term. So what we're going to do is we're going to take a series of derivatives of f. And we're just going to see where that takes us for right now. So I'll write it over here. So we start out with f of x. I'm just going to rewrite it here. And then we take the first derivative. We have the derivative of e to the x is just e to the x. And then we have the second derivative, still e to the x. So no matter how many derivatives you take, no matter how many, this is just me saying no matter how many derivatives you have, it's going to be e to the x. Okay, and then it's a maclaurin polynomial. So in all of these, you're going to be plugging in a 0. So f of 0 is just 1, because anything to the 0th power is 1. F prime of 0 is 1. F double prime of 0 is 1. So no matter which derivative, you're always going to get, when you plug in a 0, you're going to get a 1. Okay, so now with this knowledge, we can build our maclaurin polynomial. So remember, p sub n of x, that's our name, is equal to. So the first term is just regular x with the center, or not the center, the number plugged in. And remember, our number is c because it's a maclaurin polynomial. So that first term is just going to be a 1. Plus, our second term is one more derivative and increase the exponent of the x by 1. So another derivative would be f prime of 0, and then increasing the x by 1, we're just going to write in x there. So technically this is multiplied to here, but I'm not going to write it because 1 times x is kind of redundant. And then our next term, now we're taking we're at the second derivative at 0 and increasing the exponent of the x again, and then having a 2 factorial. So the second derivative at 0 is still just 1. So all we have is this x squared 2 factorial. So if you see, we increase from 1 to 2, and then we increase from 1 factorial to 2 factorial. So let's do one more. So now we have what we're going to be doing is our third factorial, but you can already kind of see a pattern forming. The third factorial, not factorial, our third derivative. And the third derivative at 0 is still just going to be 1, so that's the only part that you're really plugging in. Because everything else doesn't have to do with the derivatives of f. It's just about increasing the exponent or increasing the number that's in the factorial. So essentially what you can see is this pattern. No matter what derivative we're at, we're always going to be increasing the exponent by 1. So here we start at x of 0, then we have x to the first, now we have x to the second, x to the third. So the power of the x is increasing by 1. And then another thing that's happening is this factorial is also increasing by 1. So here we have 0 factorial, here we have 1 factorial, here we have 2 factorial, 3 factorial. So since we see this pattern emerging, we can write it as a we can write it using less specific numbers, so an n there instead, like how we did at the ends of these here. So as we can see, we have an x over some sort of factorial. And each time the x exponent increases by 1. So we're going to write an n there, because as n is just the number of times you take the derivative. So if we take the derivative 3 times, then we have a 3 as our n. And then our factorial is also going to be an n, because this is, again, the number of times you have taken that derivative. And if we have a 3 there, that's our 3, or we have a 3 third derivative, that's our n in that 3 spot. That's the 3 in our n spot. Oh goodness. So this is our polynomial, essentially. Okay, let's do a different one now. Okay. So this one's going to be a Taylor polynomial. And then we have p sub 0, p sub 1, p sub 2, and I'm going to do p sub 4. And our function is natural log of x. And we're centered at c equaling 1. So remember, this c number is the number that we plug in into each of our derivatives in this x spot. Okay. So remember, p sub whatever is just the way we notate saying this is a Taylor polynomial. So p sub 0, that means n equaling 0. So p sub 0. And we want to find the Taylor polynomial for p sub 0. Well, p sub 0 is literally this first term. Well, actually first, before we do anything, we should just take a few derivatives. So our final, our highest derivative is going to be the fourth one, because this is where n equals 4. So what we're going to do is we're going to take the derivative 4 times. So our function is natural log of x. Take one derivative, we get 1 over x. Take another derivative, we get, remember this is the same thing as x to negative first, so bring down the exponent, becoming -1. I'm just going to just write negative. And then subtract 1, so x to the second. Because the derivative of this is negative x to the negative second. And all we did was flip this -2 into the denominator. Okay. Now, third derivative. It's going to become a positive, since this is technically a x to the -2. And then decrease the exponent again. And then fourth derivative, our final derivative, is going to be -1 over x to the 4th. Oh, wait a second. I forgot you're bringing down the exponent, so... no. Okay, I'm just going to cross it out. Oh. This is actually a 2, because you're bringing down a -2 from here. And then that means this one would be a 6. Oh my god. 6. From this 3 and this 2 multiplied together. Okay. And then we're plugging in a 1 for all of those. So f of 1. Natural log of 1 is 0. F prime of 1, so 1 over 1, that's just 1. F double prime of 1, it's again 1 over 1, but it's a negative this time. Triple prime of 1, that's just 2. The fourth derivative, that's just -6. So this time we don't have a pattern like this, where all the derivatives and all the derivatives at 0 are the same. So we're going to actually have to write some stuff. So p sub 0 just means all you do is you're not taking the derivative at all, you're just plugging in that first term. So this is like p sub 0, because it's the 0 derivative. This is like first derivative, this is second derivative, okay. So that means it's going to be our f prime of c. I mean f of c. No prime, no derivative. And that's literally just 0, so p sub 0 equals 0. And then we're going to do 1. So remember, as you increase derivatives, you still have all the ones from before. You're just tacking on a new one. So we still have this f of c, but we're just tacking on this term now. So we still have this 0, and now we're going to have, we started at f of c, now we're going to f prime of c. So f prime of c is right here, which is 1. So I'm not going to write that, since it's just 1. And then we have our x minus c to the n. And we're at the first derivative, so the n is going to be a 1. And then our c is also 1, because that's the information they gave us. So it's going to be x minus 1. Let me erase this. Okay. Now we're going from our first derivative. Now it's p sub 2, so that's 2 derivatives. So that's still inclusive of everything that we already wrote. So p sub 2 is p sub 0 plus p sub 2, p sub 1, which is this one. And then we're adding on another term. So now our f double prime, because we're at 2, so that's the second derivative. F double prime is a negative 1, so this is actually not plus, but now we're turning into minus. And it's just a 1, so I'm not going to write it. And then we're increasing the exponent of this by 1. It's squared. And then we also have our factorial. Don't forget the factorial. It just hasn't shown up because it's like 1 factorial here. So now we have 2 factorial. Yeah. Okay, now p sub 4. P sub 4 includes everything from p sub 2, and then also the new term from p sub 3, and then one more term for p sub 4. So I'm just going to rewrite this because it's including everything here. And then we want p sub 3. So that's going to be the third factorial, which is this one. So now we have actually a multiplying 2 there. And then it's going to be the third factorial. I think I'm going to rewrite these so it looks more uniform. So we have a 1 over 2 factorial, and then this squared. Yeah. And now we have the 2 over 3 factorial, and then this is increasing another exponent, so now it's going to be cubed. But this would be for p sub 3, but we're at p sub 4, so we have to go one more term. So now we have the fourth derivative, which is a negative 6. So negative 6. Increase the factorial by 1 to 4 factorial. Increase the exponent of this by 1 into x minus 1 to the 4th. And that is those are our Taylor polynomials. So very simple, all you're doing is increasing by 1, and then this is increasing by 1, and then the derivative values all increasing. It's just the next derivative. So once you do them after for a little bit, you start to understand. Okay, let's see what else we've got. That's pretty much all just like this. They give you a function, they give you a c that they want you to find it at, and they tell you what they want n to be, and you just go off like that. So let's move on from this. Or actually, I'll just stop it here. This can be the introduction to Taylor and maclaurin polynomials.